defined here. But basically, throughout all my one-armed algebras will be traced. It's assumed to have some faithful normal. Say, one-armed algebra M is diffuse. These are the definitions, the bad definitions, but nevertheless understandable. There's a self-adjoining element M, whose spectral measure. So this is really actually the wrong definition you want to define. General one-armed algebra, information one-armed algebra. You can think of this as being, think of one-armed algebra as non-commutative probability spaces. This is like saying if your non-commutative probability space doesn't have the atoms.
You have to stay as central support one.
No.
You just have a chunk.
Because they have a trace. They can use the conditional expectation. If you know the relevant background, this is an exercise to think through. This is equivalent to usually that. It's not obvious, but I don't have to say something support one. So we did M is this is really interesting and non-trivial. It's not horribly difficult, but there's something interesting. So then this is finite. If there's an increasing sequence of subalgebras F, so finite dimensional subalgebras. So union. And then is dense in the strong topology on it. Strong topology being one of your choices for the relevant topologies on. And so with conjecture, well, as I'll explain, I think it's slightly different from abstract than conjecture. So it's formulated with conjecture. The conjecture says that if I take a 100 subalgebra of group factor. So if you like, just think of the one-armed algebra written by R3 semicirculars. R3 semicirculars. This is diffuse and finite. And there exists a unique intermediate subalgebra P containing this Q. So that P is maximal. So maximal with respect to inclusion among hyperfinite subalgebras. Okay. Now the existence is not hard, that's just Zorn's lemma. Okay. It's really the uniqueness. A priori, there are like tons of extensions. Okay. There's always one, it's just Zorn, that's not a problem. The uniqueness is the issue. Okay. Even the just Zorn part is like a diagonal argument. But great. So I'm going to formulate another conjecture, which is also now here. But second, seem unrelated, but what I'll briefly tell you is that they're very related. This is what I call a tensor HD for Hager congruences based on tensors. But what this says is if I take fix an R1, or actually just fix an R. So if I look at 2R independent, so these are IID, GUE, and matrices. So I have 2R of them, they're each distributed according to the GUE, and they're independent. Then whenever I take a non-commutative polynomial in 2R variables, then almost surely when I apply this polynomial to x and to 1 and so this is the identity C. one spent in zero. Yn. Okay. So this converges, and then there's complexity to a polynomial, corresponding polynomial. And here this is evaluated in the Neumann algebra generated by a free semicircular S is S1 through SR. Just free semicircles. So I should make a few comments because I realize I skipped a lot of interesting background motivation. Von Neumann algebras like hyperfinite subalgebras because we understand hyperfinite algebras. We have a hard time understanding anything else. That's a mild lie. We have lots of information about lots of other subalgebras. We understand hyperfinite algebras extremely well because of deep work of Kahn, which is part of what you got to do. So the sort of general goal to try to understand what general von Neumann algebras try to understand a hyperfinite subalgebra. Okay. So that's sort of one of the reasons this is important. There are other reasons. If you take sort of the group analog, it says that anytime you take an infinite, what's called a meanable subgroup of a free group, the unique maximal meanable group subgroup containing that amenable subgroup. Well, okay, if I say it this way, it's just sort of a stupid algebraic thing that's just true because of like when can two things in a free group generate something amenable, but it's true for lots of things that are sort of analytically similar to free groups. So there's analytic proofs of it using things like L2 by numbers you don't have time to define. And so when things are sort of true for only algebraic reasons on the group level, we don't expect them to pass the von Neumann algebra level, but if we can find an analytic proof, we sort of take the right shot. Okay. A few comments should be made about this. This is the same, I'll call this strong convergence, but this is the same as this operator norm convergence that occurred in Benoit's talk. It's operator norm convergence really plus convergence of laws. Here, convergence of laws is already just in advance. You know it for the individual side of the tensor, and then that's just sort of a linear thing. You just write your polynomial as a sum of tensors and go from there. This strong convergence is not something that you can get just from the strong convergence of the individual pieces, right? So Hager-Thom-Bjornson established this basically if I cover up one of the sides. Right? There's no tensor here, or as I say, we basically pretend that this thing doesn't exist. So the corresponding norm convergence is just the consequence of Hager-Thom-Bjornson. But when I start putting these together, it's a subtle thing. And in particular, it's actually really important that these be I. If I take xn equals yn, this is never true. Never. Okay, so it's actually really important that there be IID because we don't have sort of copy. So how are these seemingly two unrelated things actually related? Well, that's a theorem of mine. It's going to be published soon, so I guess you can say the publication. It's secretly in the future. So this tensor HT conjecture implies the Peterson-Thom conjecture. So we can reduce this interesting problem in von Neumann algebras to a problem in random matrices. Now I should maybe say a few things, even though this is more of a free probability random matrix conference. Von Neumann algebras conference is to say a few things about some of the history to this conjecture. From the equivalent formulation, I always find that with chalkboards I write smaller than it. Sorry, with whiteboards I write smaller than one chalkboard. I don't know why. So the equivalent version of Peterson-Thom is that I take a maximal hyperfinite subalgebra factor, and if I take any hyperfinite subalgebra, and its intersection is diffuse, so somehow if this subalgebra is seeing a large piece of my maximal meaning subalgebra, once it sort of sees a large piece of it, it actually has Now, why is this a useful reformulation? As originally formulated, the Peterson-Thom conjecture is conjecture about all possible maximal hyperfinite subalgebras, right? And it's not something as originally formulated that you could check in example. This reformulation you can check in examples, right? I can just take things that I know would be maximal hyperfinite, and when I'm an algorithm, plot candidates for those, and then check in those individual examples of this property, right? So there's a lot of prior work in this direction. You know, the main person sort of first thought of actual results about maximal hyperfinity was Phobos, even though that paper didn't do this because people weren't thinking about that yet. Nevertheless, the most influential book follows. Reflexivity found sort of nice ways to prove, you know, sort of generalize what Phobos did in this paper, sort of check this examples, and then there were lots of other people who did, yeah.
So cover the quantum scheme. What did you say?
So for all.
And that's something might use for the
Use contained P.
And why does it imply that P is equal to Q? Because it's kind of symmetric in Q.
P is maximal, Q is just hyperfinite.
Okay.
The real found nice ways to generalize what we did and check this examples, and then there were lots of other works following. I was listing the name. I don't want to list the various results that came out of here, but basically there's a lot of work that we would check this specific examples. So this is really specific examples. And so if you actually wanted to prove the general conjecture, this approach is not going to work unless you're somehow able to say what every maximal hyperfinite subalgebra specific factor looks like, which, you know, is hard. So that's sort of what I came into the game, was to try to find a general approach. And this is what I showed. And I'll maybe elaborate on this a bit because it really implies, you know, but
You say that something is already known about this now, the conjecture.
yes, let me address that right now.
Okay.
I want to keep these on the board for a little bit of the available board space. Recent theorem of Shervan-Blinsky and Bruno Capitan, which is that tensor HT term. Okay, I think that's the best.
Okay. Thanks.
All these conjectures on the board are true. I maybe should have erased that. Whatever, that's fine. So I'm not Shervan or Muriel, so I'm not going to say too much about the proof of this. I do want to indicate a few things that I don't want to do here, just because it is related to interesting things with random matrices. So there's sort of two important ingredients. There's somewhat technical. Well, there are many important ingredients, but let me highlight two. If you're cooking, you need all the important ingredients. I don't know that. So, one is if you remember, there's in Benoit's talk, sort of what he ended with was this estimate between Gn and G, these sort of matrix value Cauchy-Stokes transform. So let me be very vague and say in the estimate of Gn and G, G to Z, it's as there was with the quantity you had to estimate from convergence to appear in the Benoit talk. You can add a 1 over n squared. So in Benoit's context, you just do 1 over n. In my context, I'm working on n squared by n squared matrix C, 1 over n squared. You can add a term that looks like 1 over n squared e to c, where e is the Cauchy transform of a distribution on Schwartz space. And the space of rapidly increasing functions. I do not remember seeing this ever for analysis. And this is not originally due to them. This is a modification that was pointed out by Hannah Schultz, discovered by Hannah Schultz in 2003. And there's sort of a second important ingredient. Which is, well, let me not write out the full details, but when I take trace of some polynomial into GUE and something deterministic, it has some nice expansion. Let me mildly lie and actually write as infinite sum is really slightly less than that. Okay. With some coefficients. Now, the fact that this is true is not surprising, but what's important here is the alpha I are sort of really awful but explicit in sort of some three different ways. So it naturally uses the three probabilistic transform. Yes, this is a result of Felix Perron. Okay, then everything after that is far too technical to explain. But these are sort of two important ingredients, and again, I'm not going to go into details of the paper because I'm not them, but I want to sort of highlight some of the interesting methods from the random matrix framework. So what about what I did? How do you prove this theorem H22? The important thing here, what's known as the one-bounded entropy of a von-Neumann algebra. H of n. So I'm not going to give the definition again because I mean I could, but it's something you really have to practice with to understand why it's significant. But let me just say that Dima talked about this free entropy dimension. When Gillespie referenced free entropy, it's a modification of that. Now, if you remember what Dima said about free entropy dimension, a real big annoyance with it is that we don't know that it's invariant. And the one-bounded entropy is a modification of it, arguably unnatural, but nevertheless extremely useful modification of it that isn't invariant. So it can be computed on a set of generators, and if you have two different sets of generators in group one-Neumann algebra, it produces the same number. And well, mathematicians like axioms. So instead of giving you technical definitions, I'm just going to give you some properties. By the way, is there like a part of the board I should like dodging or something?
Okay, since they moved there.
Okay. So let me just list some basic properties. So it's a number which is somewhere between 0 plus infinity or minus infinity. It's non-negative if M has microstates. So Voiculescu wrote down what are now called these Voiculescu microstate spaces. If those are non-empty for sufficiently large n, then this, for every sort of fine choice of your microstate space, then this number is going to be non-negative. Because of this nib star equals already, there's some minus infinity, and that's sort of the generator. It's 0 if m is hyperfinite. It's plus infinity if m can be generated by something which has free entropy dimension, microstate free entropy dimension bigger than 1. And if you don't remember the technical jargon and what all that means, the important fact for this talk is that it's true for free group factors. So free group factors have infinite one-bounded entropy. It's subadditive in a restricted sense. It can't be subadditive, so when I write join, I mean the von Neumann algebra generated by both. So it can't be that this is just at most the sum of the entropies, because I could look at L of Z free product 1 and 1 free product L of Z. Those have entropy 0, but they're joined into something with infinite entropy. So there's a mild restriction, which is that subadditive if these pieces have diffuse intersection. So if they still are sort of somehow large intersection. And one thing I want to mention just for monomial algebra applications of this, if I look at the normalizer of the subalgebra N, the one bounded entropy of the monomial algebra generated by that plus one bounded entropy N, N is true, N is diffuse. And here the normalizer, it's like in group theory. Unitaries in M, so U and U star. So for instance, well, this is a summer school, right? So that's homework. Homework. Maybe for the monomial algebra in the room, but even if you can read these symbols, you should be fine. Prove H of M is below 0. If M is the monomial algebra generated by the normalizer of something diffuse and hyperfinite. So for example, hyperfinite is implied by being abelian, because abelian means you're somehow infinity space, and you can just chop the space up by finite time. Okay, so this reproves Voikovetsky's fundamental results that the free group factors have no Cartesian elements. But here we just get it from these ones established in general. And notice I'm saying prove these, and I didn't give the definitions. These all follow from just axiomatic applications from. So if M is generated by two diffuse subalgebras, which commute. It's generated by two diffuse subalgebras, which commute. Then it's one bounded entropy is equal to 0. And so you reprove Go's result that free group factors are what's called prime. They can't be generated by two commuting diffuse subalgebras. Prime because it means they can't be prime. Okay. Now, what's significant for us is that this naturally lends itself to an intermediate conjecture. So we'll call this H conjecture, one about an H conjecture. I should mention, sorry, I'm kind of doing a bad job. The one bounded entropy is sort of really more or less implicit in work of Kenley Jung. He didn't explicitly define it, but if you look at like the right proof, the right theorem in his paper, you can extract that you get this invariant. But it was explicitly written down by myself. And again, this sort of more these properties, again, even though he didn't precisely define them, are more or less implicit in this paper as well. And so the one bounded entropy conjecture is that if I have a subalgebra of a free group factor, then its one bounded entropy is 0 if and only if it's hyperfinite. Now, it's not hard to see that this implies the Peterson-Thom conjecture. And why is that? Well, if Q1 and Q2 are hyperfinite, and intersection is diffuse, just an immediate application of subadditivity plus this item tells us that the one bounded entropy of their join is both 0, but hyperfinite factors are free group factors are compatible, so it's equal to 0. So their join must be amenable, and therefore, if one of them was maximal amenable and had diffuse intersection with the other, their join would be amenable, and then by maximality, the maximal. So that's straightforward. And so really what this theorem of myself says is that this implies this one-bounded entropy conjecture, which I just showed you was not. So I only have 15 minutes, and I think for this crowd, it's maybe not going to make as much sense to go into sort of bloody details, although they're actually not that bloody. But let me say a few things about the proof and then try to mention some application. So I'm not going to dignify this by calling it a sketch. This is really vague idea of proof. And so there are two main steps. One is h of q equals 0 implies, and this uses exponential concentration of measure for the GUE. So if I take a sequence of subsets of 2R copies of n by n self-adjoint matrices, then I put that with the 2R fold power of the GUE distribution. So if I take some sequence of subsets that are Borel and have measure at least a half, then for any epsilon, they're epsilon neighborhoods that measure at least 1 minus some decaying factor, which decays like exponential minus. So this implies some kind of microstates collapse. And this is where it's a little technical to define because I can write, say, generators. Again, I might reduce the case to generated. I can write generators for my algebra, but they can't be expressed as polynomials in semicirculars, right? But they can be expressed as some kind of function of the semicirculars. And maybe let me say it like this. Maybe we'll talk about what I wanted. So I write this kind of very general function. Semicirculars. For most choices back then, yn. So if I look at if I apply a function to these xn, yn, so some very general function that exists because David Jen was on function calculus. So for most choices, these are almost unitary. So there's a lot of epsilons flying around. What would like be the epsilons like? And so this is sort of microstates collapse. You try to sort of take your microstates, your approximations for your semicirculars, and use them to induce approximations for your subalgebra. If it has one bounded entropy 0, then all those microstates sort of collapse under one. And this was sort of already exploited in a different vein by work with myself, David Jekyll, Fred Nelson in the room, and Thomas in a different context. Okay, so that's by now not trivial, but still well-trod path. You know how to do. And the second, this is where it gets again also some technicalities under the rug. With sort of various nice approximation properties. Well, actually, just one approximation property of the Caesar algebra generated by a free-semicircular family. These are three independent spectral measure one we know above, pi, sort of function minus 2 dx. Actually, is that correct? And the relevant approximation property here is local reflexivity, which again I'm not going to define for again, if you're an operator algebraist, you've probably heard of it, maybe you don't remember it, but if you're not an operator algebraist, it's not going to make much sense. And cheap amount of time. But the fact that this is true is a combination of work with Kierkegaard from 80s or something. Yeah. Hertford, 94, and work from Ken in 4. So basically, there's some nice way to approximate your knowledge in your von Neumann algebra and sort of push them down to the C-star algebra. You sort of need that because, well, I erased this tensor HT is the thing about operator norms, and von Neumann algebras are things that care about strong operator problems. So you have to reduce this von Neumann question to the C-star question, and that's what local reflexivity allows you to do. And so what this says is that if on the other hand, I take even say non-random tuples like this, and for technical reasons, I have to take transpose, and if this converges strongly, and then goes to infinity to s to 1 s off. Okay, then no non-meanable. So, the microstate's given, so this approximation is given by x and yn, don't collapse q whenever q is not. So the reason I'm writing it this way is that this is actually secretly a deterministic statement. Not even, you just write down a statement that's just about strong convergence of matrices, and you can write a theorem that says they don't have this collapse. Now, I didn't say what collapse meant, but again, it just there's like a bunch of epsilon flying around. Just said this is the essential idea, is that after a while, they're not almost material. And this is, once you sort of realize that it should be true, is not actually so bad to prove. Again, I skip the technical detail until you have at least 5 minutes or so to get some applications, but this uses methods not coming from probability, but coming from definite infinity. There, 13. One other thing is reading. Oh yeah. So there's many ways to characterize the non-amenable in terms of sort of they're nice after operators and normal. Okay. So maybe let me just mention some applications. They're being 6 minutes. So if you take these properties for granted and you look at this one, well, then this tells me that if I look at the amenable subalgebra and I look at the von Neumann algebra generated by its normalizer, it also has one bounded entropy plus theorem, right? And so by this characterization that's equivalent to amenability, what we get is that the von Neumann algebra generated by the normalizer. Sorry, I said amenable, I meant hyperfinite. And that's also what non-immutable means, not hyperfinite. Sorry. Yes. Whenever n is diffuse and hyperfinite. So we take something diffuse and hyperfinite, then look at the von Neumann algebra by its normalizer that's also diffuse and hyperfinite, and this is what's known as strong solidification. And it was originally proved by Ozawa-Popa using deformation. And this is now sort of frequently cited and often celebrated results. We now have 3 probability. But we can do much better. I can essentially, maybe in the interest of time, not write out the bloody definitions and just mention it for the people who know about these things. In von Neumann algebras, sort of motivated from geometric group theory and things that naturally show up in cohomology and study of subfactors, we like weird normalizers. We have this plain vanilla normalizer, right? Where we can like put some sprinkles on it, and we can talk about like quasi-normalizers, sort of like an algebraic version where, well, this is algebraic sort of in the sense that the quasi-normalizers form algebra. Instead of saying that UN U star then, you would say something like, if we look at nxn, that's finally generated. If you look at the nn bi module generated by x, that's finally generated as like a
left-hand modulus. And so that would be such active would form the quality normalizer. I can modify this a little bit, and instead of saying equal, say that it has diffuse intersections. Instead of equal, I just sort of say intersection large. That's what normally the W normalizer. And I can just do word for word the same theorem with one-sided with this normalizer replaced with weird normalizer. So you get some sort of like negative. Because let's just pass along bad names. Replace these normalizers with weird normalizers. And in fact, one of the sort of major pieces of my previous work was finding some sort of analytic version of like the weirdest possible normalizer that contained all the other normalizers. And you can do it for that, but yeah, it's a bit of work. And for those in the know, again, this is maybe the wrong crowd for this. There's going to be at least a few people for which this would be interesting. If you like, I can be even weirder and take the von Neumann algebra generated by the normalizer inside the ultra power and then intersect back with my original subalgebra. And I can do this also for all the weird normalizers. So you get, ultra filters are usually denoted not their others by omega, so you get omega. Stuck in a joke. Oh yeah. How about ultra filter? Yeah, that is better. But this is funny. Let's see. Maybe let me mention one more application. In von Neumann algebras, people like studying maximal amino subalgebras, maximal abelian subalgebras, sort of like looking at a diagonal inside of matrices. So another application that we done prior work of mine this is a maximal abelian subalgebra. And it's also maximal hyperfinite. Well, I know abstractly that A is isomorphic to L infinity functions on the interval. Okay. And I have these left and right actions of A on bounded operators on L2 of FR orthogonal minus L2 of FR. So I'm skipping some things here, but this trace gives you an inner product which complete to get what we call L2 space by copying the L2. Okay, and there's this thing called the conditional multiplication, which it does what it does in classical probability theory, and it's just the orthogonal projection, and you can look at things whose projection is 0. That's what this is here. So these left and right actions are acting on the left and right. And just from general spectral theory nonsense, I know that the von Neumann algebra generated by this left and right action is some L infinity functions on the square with some measure whose marginals are absolutely continuous with respect to the big measure. But the measure could be sort of like discrete in some direction, but it just projects onto the axes on the Lebesgue measure. Except where that doesn't happen because corollary you get from this and prior work of mine is that nu is absolutely continuous with respect to two-dimensional Lebesgue. Now there are, believe it or not, non-abelian versions of this. It's just sort of saying something about the the bimodule structure of the orthocomplement bimodule subalgebra. And you can also say that if you have something maximal mutable and you look at this orthocomplement bimodule, same thing, just because L2 of A is L2 of that subalgebra, then has a bimodule that's contained in the direct sum of the course. Okay, now I'm getting a little in the weeds, but it's some non-cutive analog of this statement, and it's like a left regular representation. So I think I'm basically out of time. There's other things I can mention, but I'll stop.